Actually, as we can see, so we have a vision lab here. So I can see Eric Polster, one of our collaborators here, actually. So I'm talking about a topic, one of our projects. It's more applied science and applications, and a little bit different from health science. Actually, Anne, actually, it's a beautiful message we received this morning, actually. I really like it. So we are going to follow some of the messages which you conveyed here. So here, we are totally transforming to a different topic here. It is not related to health science, but we are related to something protecting humans from outside, from intrusions, from attacks. So what we need to do is this vision lab. Basically, we have. If I summarize, I'm taking 1 minute to make that transition from health science to electrical engineering, basically. So here, this is the general activities going on in this group with all the graduate students who are participating in different activities here. We start from the data acquisition. So totally external. We use cameras and other sensors to grab data and process this data to make some meaningful interpretations. So basically, if you are talking about the wide area surveillance kind of environment, we have lots of data captured, and then we need to pre-process it in order to avoid some kind of distortions due to the environmental distortions and device distortions and all that. So here you can see that distortions due to haze, fog, lighting, and rain and all that. This is totally an external distortions introduced into the data. And then we make some meaningful interpretation. That is, we have to extract the information from the data and then interpret appropriately based on the application, what we want, whether we want to detect an object or identify an object or identify an individual or identify the behavior of an individual or an action or expression or whatever. That basically depending upon, including the intentions. So depending upon the application, we need to make meaningful decision making. So from data acquisition to decision making, that's about basically all the projects, all the research activities going on in this vision lab. So here, in this specific talk, what I am talking is basically on an application to detect and report the intrusions on a pipeline right-of-way, that is oil pipelines around everywhere, all over the world. In the United States itself, we have about 2 million miles of pipelines passing over different areas, different places, because without this gas pipelines, we cannot get gas to our location. So it is there everywhere, from the larger pipes to the smaller pipes, everywhere. So in this case, what happens is there are pipeline right-of-ways. So it looks like a free land. So the construction people or whatever, there may be intrusions, there may be somebody parking large vehicle over the pipelines. What happens is that will be crushing the land and destroying or destructing the pipes, and then the pipes may break. It may lead to some kind of leaks, which the pipeline companies, oil pipeline companies may not like it. And in addition to that, it is an external problem because leaks may extend to the plantations and the green areas there, that the plants will be destroyed. Plus, sometimes it will be leaking towards the water resources. That will be another problem. So it is an environmental issue also. So what we are asked to do in this particular project is, actually, we need to automatically detect and report the location and the type of equipment or any intrusion happening on the pipeline by analyzing the aerial imagery. So the agency will be supplying these images captured by this manned or unmanned aircraft flying over the pipelines, and then we need to automatically detect and report the location and the type of intrusion happening at anywhere in this country. So here, actually, what happens is this data will be captured by flying aircraft, maybe manned aircraft or sometimes unmanned aircraft. So the altitude, the environmental conditions, background locations, and they will be supplying terabytes of data. A human analyst will find so difficult to find one location where one equipment is there. So by the time he keeps scanning through the frames and frames and frames, sometimes one frame will be there is an equipment, so there is a possibility that people will miss that, the presence of an equipment, so or an intrusion. So that's what the importance of this one. So automatic analysis, the system will not become fatigued. We will not miss an object. That's the reason why we are asked to do this particular project. So the idea of the initial application is actually detect this kind of equipments, construction equipment. There are lots of construction vehicle parking over the pipeline right of way. So we need to analyze the data and detect the presence of this kind of equipment. So we are getting this kind of images. Actually, there is one equipment here, so we need to keep analyzing the frames and frames of data, and then we need to see if what kind of equipment at which location. We need to find out the presence plus the severity of that the equipment, presenting an equipment at that location, or having an equipment in a region right over the pipeline, or it's farther away from the pipeline, or if that equipment is active or not. So depending upon that, if we are reporting that, hey, there is an equipment which is active over the pipeline, somebody should immediately go and remove it. If it is farther away from the pipeline, is moving towards, you can have some time, but depending upon that, we will be able to have some kind of severity measures or risk parameters which we'll be able to report to the agency. So these are all some of the data which we have. Why I am showing this is because these are all captured by different aircraft, different sensors, different locations. So the colors will be different, the type of data which we are receiving will be different, size of objects will be different, even because of the altitude of the flying aircraft with respect to ground, and so on and so forth. Then other tasks like the lighting issues, the shadows, illumination problems, overexposures, which is as bad as the lighting, low lighting, and sometimes the occlusions, overhanging vegetation there, the scale because of the altitude, then the resolution because of the type of data acquisition devices. So all these tasks have to be handled in this process. So what we do is we go for an improvement of the visibility, whether it is a low lighting or high overexposure or a resolution deficiency or whatever. We need to improve the visibility of the image first, and then we need to extract the features extract meaningful features from the data, and then we need to go for some kind of a what is called keyframe detection. For example, if a aircraft is flying over the pipeline right of way, it may go through a lot of area where there may not be the presence of an object because it is going for a farmland or something. There is nothing. So in that case, there is no point we pay lots of attention to every frame. So first of all, we will see which are the frames which we need to really consider, pay more attention to in order to extract the features to identify an object. So we extract the key frames first, and that means thousands and thousands of frames can be eliminated because those frames are not making any sense. So just do an initial search and then eliminate those. And then when we find some key frames, pay more attention there and extract the features of every corner there, and then find out whether that's an equipment or not, or a device of interest or not, or object of interest or not. And then background elimination, and then go for extracting the features, because when we look from the top, the equipment may appear in any direction, any viewing angle. Sometimes the flight will be going on the left side of the equipment, or sometimes right side of the equipment, sometimes just above the equipment, and so on and so forth. So in all these cases, we have orientation issues, size issues because of the altitude, and rotation issues because of the direction of the equipment which is appearing on the scene. So the technology should be really a kind of a rotation invariant, size invariant, and lighting invariant, and then orientation invariant, and so on and so forth. And then we need to assign the priority, threat priority, and report. That's what exactly the overall flow of this system. So here, when we go for the enhancement first, I'm going to tell you, this is actually from a blurred data, we need to enhance the data. So we have an enhancement algorithm developed in this group by some of our candidates here. And then that image, that system, what it does is it extracts the information of every pixel in the image, and then with respect to its neighborhood, it assigns a particular transformation function to improve the intensity or reduce the intensity. Improve the intensity of a darker area, you reduce the intensity of an overexposed area, or don't do anything for a normal visible region. So those kind of activity will be automatically done by the algorithm. So it creates an image like this. For example, if this is an input data, where the algorithm will be able to generate this kind of a natural data. So from this one to this one. So from here, this is an example where one person is actually in a visible region, somebody is hiding. So both can be made visible. In this case, it is reducing the intensity of this region. Likewise, this technology will be automatically doing this and visibility improvement. And that is applied to this kind of pipeline data, so we can get a better visibility for all the images which we captured by the aerial systems. And then we go for the unwanted areas in the images. That is our interest, basically. So remove the building areas. There is no threat object in the building area because no pipeline is going through the buildings. So trees, and then roads, plain ground, other objects which are appearing in the scene. So all those should be eliminated because we can go for the points of interest. That is the key locations where we need to pay more attention. That's what exactly the algorithm does. So the background elimination, so most of the backgrounds will be eliminated. Only the regions of interest will be staying there. So here there is another method. This is actually done by a machine learning methodology. The system will be trained to detect whether that's an object of interest or the region of interest or not. So that system will automatically take care of that the distinction between the regions of interest and not. So that only the regions of interest will be staying. That is, for example, the house, the background, the regions of residential areas are eliminated. Only these regions where likely to be the object presence is retained. And likewise, the most of the regions can be eliminated by this machine learning technology. And here also we eliminate most of the regions, about 90% of the regions can be eliminated. These are all done automatically by the algorithms. So here, and then the advantage is actually we need to search only this eliminated, the remaining area in order to find out whether there is an object of interest or not. Then the background elimination. These are all some of the examples which I am showing. So here the next part is once we have a regions located, we need to find out whether that region makes any sense in terms of the presence of an object or not. So what we do is we went for a path-based model, because when there is an overhanging vegetation which is the covering or making occlusion to an object, there is no point searching for the entire object. For example, if one of our friends actually wearing a sunglass, we will not look at his eye features to extract his the identity. We look at other features. The occluded features we automatically avoid, and the available features will be given more priority or more prominence, and then we extract the features of that and give more weightage to the available features to identify whether that's a person whom we know or not. So that's exactly the same methodology here we used. So we divide the entire regions into different parts, and if the parts actually which are not making any proper information, then we eliminate that and reduce the weightage for that region. If the regions are more available or making more features there, give more weightage to that. So it's a weight-based, part-based approach, so weighted approach. So that's what exactly the technology which we used in order to avoid the occlusions in the object, so that we will be able to accurately detect the objects in the scene. So here, again, this is about the division technology. The whole region will be divided into different parts and give appropriate weightage to each part depending upon the visibility. Another important aspect is actually when we look from the top, it is the objects may be in different locations, rotations. So in that case, there is no point we go for dividing the image like this, the rectangular blocks. Instead, we found that making circular blocks will be making sense because each ring, whatever the location rotation or the direction in which the object appears, that ring stays as such. So each ring will be considered as a block instead of considering the rectangular blocks as in our previous case. So this is what our new another contribution to this group actually, ring-based approach. So that each ring, whatever the direction the object is appearing, so that ring makes sense. So that's an idea where the features are extracted for that rings and then make the ringlet, we call it ringlet intensity distributions to identify the objects of that interest. So here again, these are all some of the details of this ringlet approach for detecting objects with the different rotations. And these are all some of the examples we have. Actually, so this is a raw image. After background elimination, we have this. And then after the detection, we have the object detected there. And then this is another image, background elimination. We eliminated almost 99% by eliminating the background. So only 2 blocks we need to investigate further. That's a detection. Then we have went for another step. Once we detect the object here, what we want to do is, how about the severity of that object? That means what happens is, if that object is right over the pipeline, or it is farther away from the pipeline, or what kind of object is that, whether it is a heavy equipment or a lighter equipment, or that is an active equipment or not. Active means it's moving or not. Somebody is doing something there. So in that case, depending upon all those information, we assign a priority to that threat. So then we inform the agency that at this location of this country, and an equipment is there, and this is the percentage of risk priority there, or threat priority there, because that is an equipment right over the pipeline. That's a large equipment. If it is staying there, it's going to be making a lot of trouble to the system, so it is better go and remove it. So that kind of information. So immediately we pass that geolocation of the object and the size of the object and the activity of the object, whether it's an active or not, and then we give the risk priority information to the agency. That's what the overall project. So then these are all some of the examples. The risk priority is totally determined by the location information to the pipeline right-of-way information. These informations are available, and then based on the distance calculations, we provide the distance and the heat parameters. By using the infrared data, we will be able to know whether that is an active device or not, and so on and so forth. And by our analysis, we know what kind of equipment is that. So this is about the overall flow diagram of the risk priority assessment. If we find an object here, the background is eliminated, part-based model that is for occlusion elimination, and then if an object is not found, repeat for another frame. If an object is found, go for the heat information and the mapping, that is a location information. Finally, we go for a risk priority assessment. That's what exactly the reporting information. So there are some examples here. There's a high priority depending upon the location and all that. So we provide the priority too. So this kind. So again, another example. These are all the different types of sensors here, skid steer, and then that's an overall the hardware acceleration, because our system is actually integrated into the camera and a flying aircraft, and we are testing at different locations. And we already tested at the Gary, Indiana, Philadelphia, and then West Virginia, and then Boston area. See, the 4 experiments have already been done, and then the system should run in real time. So that means we cannot leave it as an algorithm in a computer. So what we did is actually we have a laptop with other hardware like GPUs, that is a graphical processing unit, integrated with that. So if you look at that architecture, we see some portion of the algorithm flow will be done in Python and C++ and so on and so forth, and with the different methodologies, and we integrated the whole system, and then made a single package and give to the agency. They can fly in the aircraft, and then and there, when they find an equipment on the right of way, that means the system finds an equipment on the right of way, the system reports. So that's the idea. Then, in addition to that, we used this in a UAV, that is an unmanned aircraft in West Virginia, it flying over the pipeline right of ways, and then reported the information. It's pretty much accurate. Here, actually, it is more than what expected by the agency in our proposal. So it is pretty good. It is moving forward. Now we are actually moving towards analyzing, instead of having aircraft data, we are analyzing the satellite data, because to detect and report the presence of any kind of intrusions on the pipeline right of ways is going on. And another project which is associated with this is to find out the building change detection on near the pipeline right of ways. What happens is they observed that some of the apartment complexes near the pipeline right of ways, on the backside it is going to be pipeline free land. They just extend the construction, maybe making another block to the pipeline side. Or sometimes a 3-storied building become 4-storied or 5-storied building. In that case, what happens is that region will have a force, put more force into the ground, and then that's going to make some kind of deflections to the pipeline. So that has to be reported. So what the project is change detection, building change detection near the pipeline right of way. So the aircraft will be flying once in a while, maybe once in 6 months we will be getting data. So what kind of changes happen to those buildings on the right of way region? So that has to be reported, so the agency can take care of those things.